Hey guys, this is Mr. Sal. We're going to look at solving with logarithms. Alright, 6.6, uniqueness of b to the power of x, which is just the same bases. If the bases are the same, the good news is that we get to ignore them. However, they won't show us all the time that the bases are the same, which means we have to do some work on that, or let the calculator do it, whatever. If b is greater than 0, then b does not equal 1, and b does not equal 1. Then b to the power of x equals b to the power of y is equivalent to x equals y, because if we can get those exponents to be the same, then we'll get the same value, which would give us a true statement. That's pretty nice. I don't know, I guess we can demonstrate this. Right, like if I had 2 to the power of 4 right here, and I said 2 to the power of x, solve for x, or it equals 2 to the power of x. Well, what value of x would make this 2 to the power of 4, which is 2, 4, 8, 16? Yeah. Well, that would be 2 to the power of 4. So x is 4. Now, maybe that's oversimplified. However, let's say that we didn't see that stuff from the beginning, right? Let's say that we changed this, and we said 16 equals 2 to the power of x. Okay. Well, we could figure out how many times 2 multiplies by itself to get 16. In fact, that's not too bad. But if we do that, it's just going to give us 2 to the power of 4, which equals 2 to the power of x. And what that says at the bottom is if we get that, then we could ignore the bases, and we just got 4 equals x. Bam. Well, what if it was 2x? Well, 4 would equal 2x, then x would equal 2. You guys see where I'm going with that right there? So it can change, but if the bases are the same, just get rid of them. So let's look at these examples right here. I've got 5 to the power of x equals 125. And what I'm going to do on this is I want base 5 on this, all right? So I'm going to change 125. I'm going to divide it by 5, which will be the base, and that would be 25. 25 splits up into 5 and 5. So 125 is really 5 times 5 times 5, which is 5 to the power of 3. Now this equals 5 to the power of x. The nice thing about the same bases, and that's what this property is telling us, is I can ignore the bases and focus on the exponents. So in this case, x is 3. And you could check. 5 to the power of 3 is 125. The same principle for this next one, except for I can't split up 8 into just 4, right? Because it'd be 4 times 2. Here's my base 4, but it's not 4 to some power, right? So what I've got to do on this one is I've got to change the bases, both of them. And I'm going to start with the 4. I can change that into a base 2. So that would be 2 to the power of 2 to the power of x. And this would equal 8, which is 4 times 2, there's my 2 there, and my 4 would be 2 times 2, which is 2 to the power of 3. Now at this point, I've got the power of a power property for exponents, so I'm going to take the exponents and multiply them. So that'd be 2 to the power of 2x equals 2 to the power of 3. And now my bases are the same, so I can ignore those and rewrite this as an equation, 2x equals 3. And solving for x, all I would need to do is divide both sides by 2. And then I get x equals 3 halves on this. So 4 to the power of 3 halves is 8, and you could check that in the calculator. Just you may need to put parentheses around your answer there. Use the like basis property to solve this equation. Okay. So, you know, if it says this on the homework, then you could use logs just to check, right? Which we'll do at the end of this one. But it wants us to use like bases to solve this one. So, from this, I'm going to need this to be 5 to the power of x equals another base 5 to some power. Now, I don't know what that power is to get 625 yet, but we'll find out, okay? What I'm going to do is I'm going to break 625 up, and I am using a factor tree. But it's not a prime factor necessarily. I'm just looking for base 5 values. So I'm going to take 625 and divide it by 5. because it would be 5 times something. And when I do that, I get 125. Well, it ends at 5, so I know it's still divisible by 5. So that, back to this point, 125 actually be 5 times 25. Well, it's good. We know we can't really check with the logarithms now. Sorry, 25 isn't circled, because we can divide that by 5 as well. So that's 5 and 5. Okay, that changes things quite a bit. So that's 5 times 5 times 5 times 5, which is 5 to the power of 4. So 625 is actually 5 to the power of 4. Once again, ignore the bases, and we got x equals 4. Done. All right, in this example, we have base 2 to the power of 2 times quantity 3x minus 7 equals 2 to the power of 5 times 2x. Well, good news on this one is that the bases are already the same, which means we could ignore those, and we can rewrite this. And this is now just an equation that we can solve. So we'll distribute the 2, 6x minus 14. 5 times 2x would be 10x right there. And I'm going to choose to put the x's on the right, so I'm going to subtract my 6x from both sides. So I got negative 14 equals 4x. And we'll divide both sides by 4. And we get x is a decimal value on this one, negative. I'm okay with improper fraction, as long as we simplify it. So we don't want to keep it as negative 14 fourths. We'll divide those both by 2. So negative 7 halves would be our x value. Now this is just like a regular equation. We could check this. So I've got 3 times negative 7 halves minus 7 times 2. So yeah, that would work. 2 to the power of negative 35. And 5 times 2 times negative 7 halves would be also negative 35. So 2 to the power of negative 35 equals 2 to the power of negative 35. And, well, that checks off for us. Use the like basis property to solve this equation. So once again, logarithms won't do now that we've learned how to do it yet. But what we need to do is take 81. Now we could say, well, I want to take 81 and break it up into thirds, but actually I want to break it up into threes, and I'll show you guys why here in a moment. So I've got 3. 81 is divisible by 3. That'd be 27, which is also divisible by 3, and 9, which is 3 and 3. So 81 is actually 3 to the power of 4. Now, right now, this equals 1/3 x. 1/3 to the power of x. So the bases kind of look different right now, but we can make them the same, and we can do it one of 2 ways. We can change 1/3 into a base 3, or we can change 3 into a base 1/3. And the truth is, we get to choose, but it doesn't really matter. Just if we do it, if we change either one, it's going to change its exponent to a negative because we've reciprocated it, okay? All right, so class's choice, we are reciprocating 1/3. So what does that do? It makes this positive 3, or just a 3, not a fraction anymore, but it makes the exponent negative. So 3 to the power of negative x equals 3 to the power of 4. See, and what this has done now is even though it changed the exponent to a negative x, the bases are the same. So we can ignore them. And so I have this new equation, negative x equals 4. And to solve this one, I'll just change the signs on both, or divide both sides by -1. And we get x is -4. So, again, we could check this one. It would need the 1/3 in parentheses. And I would have in parentheses 1/3 on my calculator. But then I need an exponent of -4. And when I do that, I do get 81. So that checks off. And it's a good example. Let's go back to that 1/3 to the power of x equals 3 to the power of 4 stuff. Let's say that I reciprocated the 3, all right? Well, that 1/3 to the power of x stays, and this one is kind of a shortcut as well. So I'm reciprocating the 3 into 1/3, but when I do that, it makes my exponent a negative 4. Well, since my bases are the same right there, I just have x is negative 4. So it kind of confirms what we already knew. X is negative 4. All right. Now with the base 2's, the 2 problems ago, it was quite generous for us. However, now the bases are not the same, so we've got to make them the same, right? How? Now remember, the idea is to get the bases the same, right? So even if I did divide both the bases by 4, I'd have one base that is 1 and another base that's 4, so they're still different, right? So in general, just a rule in general, if we have let me start that over, the bigger number, the bigger base, generally simplifies to the lower one on this, generally, okay? If they don't, then they're simplifiable to an even lower base, which these two are. But I could make 16 a 4, right? So let's just look at 16 for now. 16 would split up into 4 and 4. So I'm looking for base 4s right now in this case. So that means that 16 by itself is 4 to the power of 2. Now that had an exponent of 2x plus 4. And this equals, well, we already had that base 4 to the power of 3x minus 7, right? Now we have the same bases, kind of, but I have that red base 4 to the power of 2 in parentheses. So this goes back to exponent operations. That red 2, how is it related to the black 2x plus 4? Let's look back. That would be, you guys remember this? 3 to the power of 6 to the power of, I don't know, 2. You guys remember what we did with the exponents? Let's look. Right, you could have 3 to the power of 6 times 3 to the power of 6, which gives us how many 3's? 12 of them, right? So what would we have done with those exponents before? Multiply, right? So if we were multiplying those, then we're going to multiply these, but it's multiplying everything. So it's really kind of like distributing this 2 into that set of parentheses. So it ends up being 4 to the power of 4x, x, and then 2 times 4 is 8 right there. And that equals 4 to the power of 3x minus 7. Now that we have the same bases, we could ignore that stuff. So what we end up with then is the exponents, 3x minus 7, would equal 4x plus 8. And this is changed from an exponential equation into a problem of just solving an equation. So I'm going to put my x's on the right by subtracting 3x from both sides, but also subtracting 8 from both sides. And I've got negative 15 equals x, which is my answer on this one, and we should check on this. Which you'll need a calculator to check that. 16 to the power of 2 times negative 15 plus 4 would be the same as 4 to the power of 3 times negative 15 minus 7. Now I did say there was a different way to look at this, and we didn't need that stuff in the beginning there. That was just an example. The 4 and 16 can also be separated into 2's, right? So this 4's right here I could change into 2 and 2, and this one as well into 2 and 2. So that means 16 would be 2 to the power of 4, and then that would be to the power of 2x plus 4. And this would equal 4, which is changed into just a 2 and 2. So that gives us the same base, 2, but it's 2 to the power of 2 times that 3x minus 7 from the exponent. Now if you solve this, you'd get the same answer. But again, it's just to point out that it doesn't matter which way we use or which base we use, as long as they're the same, then we can get rid of the bases and just focus on the exponents to solve. All right. Solve for x, round answers to the nearest thousandth. All right, looks like we will learn how to use those log stuff. All right, so we do need to change this into a log. So I've got my log, my base on the exponent is the base for the log as well. And it's the log of whatever the answer of my exponential form was, which was 43. And this equals my exponent, which is x. Now again, some of you guys have a way to put this directly into the calculator, just as we see it. Log base 3 of 43, push enter, and you're good. However, mine doesn't have that. So we've got to figure out a different way, and that is the change of base property for exponents. So the way this works is we're going to change the base into either natural log or common log, even though it could be whatever base we want. So when this happens, we got the natural log divided by the natural log of, we'll start with what it was the log of, which was 43. And then the base goes in the denominator, which, I don't know, we could kind of consider the basement. And this is the natural log of 43. So the natural, I'll just type this in, natural log of 43, close my parentheses, divided by the natural log of 3. And then I push enter, which is 3.4 thousandths, tenths, hundredths, and then I've got 3.5, so I'm going to round that 3 up to 4. There we go. And that would be my answer for this. Now I did say it didn't matter what the base was. With the natural log, we've changed the base into an e base. However, if you wanted to, you could find, and you could type this into the calculator, the common log of 43 divided by the common log of 3. It will give you the same answer either way. So when we see problems like this, it really comes down to a question of which button do you want to use. And if the log button is more convenient, then use that one. If the natural log button is, then use that one. All right, round answer to the nearest thousandth. So this one, I mean, we could try it. We could say, well, I want 65 to be a base 7, but 7 doesn't go into 65 evenly. So that method's not going to work on this. But if we do change this into a logarithm, then it should work. So I'm going to change this into a log of base 7 of the 65 right there. And this would equal the exponent, which was 8x minus 3. But we are solving for x. So I'm going to change this, the base of the log. You guys want common or natural log? All right, so common log. I've got my common log of the 65. And we're going to divide it by the common log of 7. Now again, this equals 8x minus 3. So I'll type that into my calculator. All right, so dividing the logs, that's what I get. 2.1452, but we only want this to the nearest thousandth, so I don't even need the 2 on that. And I wouldn't need to round the 5 up. So it'll stay that way. But to solve this thing, we'll treat this like an equation. So it looks like I'm going to have to add 3 to both sides. And then I would divide both sides by 8, which I'm just going to put in my calculator. 0.6. Again, we're just rounding to the nearest thousandth, so 0.643. 643 thousandths. But again, let's just put this into the calculator. So I've got 7 to the power of 8 times 0.643 minus 3, which is 64.8. So why is it different though? Because we rounded. We use some rounding. So it doesn't have to be exact, especially after we've done some rounding. All right, if e to the power of 7x equals 35, then x equals something. And again, we'll round this to the nearest thousandth, or third decimal place. So my e to the power of 7x equals 35. I'm going to change that into a log. And my base is e, which is good news. Log base e of 35. This would equal my exponent, which is 7x. Now that log base e could be changed into a natural log right now if you wanted to. Just the natural log of 35 equals the 7x. So in my calculator, I've got the natural log of 35, which is 3.555348061, whatever, we'll round it. We'll go to the 10,000ths on this one. This equals 7x. So to solve for x, we'll divide both sides by 7. And that gives us 1x equals, divide by 7, 0.5079. So I'm going to round that up to 0.508. Which, once again, we can check. E to the power of 7 times that stuff equals 35. Use the like basis property to solve this equation. Here's what can't happen if we see something like this on a test, all right? Is we change this to 15 to the power of x equals 32,805. But the question is why? Why is this bad? Well, we didn't change the 32,805, but we did change the base, right? Why is it that I can't multiply 5 and 3? Well, to answer that, we got to go way back, and that is the order of operations, right? We can't start multiplying bases until we get rid of exponents. And right now, we still have an exponent. So we can't do this, right? So never do that. So if you have something multiplied by a base with an exponent, don't multiply the two together, okay? However, we can get rid of the 5, which is nice, by dividing, just like we would an equation, both sides by 5. Well, then I've got base 3 to the power of x, which is good, and you can have it in parentheses if you want. But I've divided 32,805 by 5, which is divisible by 5 because it ends in 5. So what would that be? 64, 65, 61. All right, here's the good news about this, and they did tell us to use like basis property. So I've got to change or split this 65, 61 up into 3. So I'm going to divide it by 3, because if I can get it to be the same base 3, then I'm in good shape. Which would be 21, 26, 4, 2187, looks like. And this is divisible by 3 because 2 plus 1 plus 8 plus 7 is 18, which is divisible by 3. So we'll divide it by 3 again, which would be 729, which is also divisible by 3, by 243, which is still divisible by 3. Oh man, 81, and run out of space. Nope. Okay. So 81 would split up into 3. Oh, and 27. That's better. Which would split up into 3 and 9, which would split up into 3 and 3. So it's a lot of 3's, which is okay. So I've got that 3 to the power of x equals 6561, which is simply 3 to the power of 1, 2, 3, 4, 5, 6, 7, 8. 3 to the power of 8. Ignore the bases. And we get x equals 8. Now again, just because of the way I've done it today, I'm going to check. 5 times 3 to the power of 8 is 32,805. And it just, I don't know, allows me to box that in with a little bit more confidence. So let's say that we go back to this point right here. Then I could change it to a log, which would, I think it's kind of faster, right? So that'd be log base 3 of the 6561 equals x which is where math people felt like it saved so much time. But just to put in the calculator, I would use the change of base stuff. So I think we used logs last time. We'll use the natural log this time. Natural log of 6561 divided by the natural log of 3. And when I put that in the calculator, it gives me 8. The change of base stuff with the logs, I would only use that to check my answer, not to find it, because we need to see the log basis stuff on the test, if it asks for it.